For a quick introduction, thank you everyone for joining this session at large. So, without wasting further time, I'll just get started. Uh, Give me a thumbs up if you're able to see my screen.
We can see your screen.
Okay. Okay, so let's get started, right? I think most of you have heard about lakehouse, right? And most have heard about ETL. So ETL is basically extract, transform, load. It's a three-phase process where we extract data from operational systems and basically cleanse it, transform it, and bring some valuable information about it, right? So I will go ahead to the whiteboard. I prefer explaining the whiteboard. So yeah, you see my screen. How many of you guys shop at Amazon or Walmart or any website? Many guys, I think, shop. We'll take that example to explain you in details. So when you shop at Amazon, let's say Amazon, we simplify example, since most of you shop at Amazon. So in Amazon, you have a website, right? You go to the website, you add items to the cart, and you place an order button. And anybody, like, how what happens at the back end? So back end, we have different systems. Like, we have the order system, we have the fraud system, we have the inventory system, we have the return system, or we may have the tracking system for delivery and shipments, right? So all the systems are system designed well for performance, and they talk to each other via APIs. And these systems are known as operational systems. Why operational systems? Because they are responsible for day-to-day operation of the company. The day-to-day operation in this case is taking orders, shipping, delivery to the households. Right? So what happens when you click the order submit buttons? In the back end, the first step is doing a fraud check. A fraud check happens, a transaction is created in the fraud system. The via API, the message is passed to the order system. Sorry, the API, the message passed to the inventory system. Inventory row is depleted, inventory count is decreased, and then eventually there's an order transaction created. So in case of returns, there could be a return transaction as well if you're using that website to return some items. So all the systems talk to each other by API, and these systems are also known as OLTP systems. Why OLTP systems? OLTP is online transaction processing because they work on very few rows. Very few rows, like in case of an order, you may at most have 100 items on the cart, or maybe 50 items. In generally there'll be less items, 4, 5, 1, right? So they just work on very few rows, and they are designed for write speed, right? Because the response after you click the order submit button, the order submission, the confirmation has to happen within sub-seconds, right? So that's the reason the system are designed for write speed, because they have to quickly write orders records. They have to quickly decrease the inventory in the inventory system. They have to do write a fraud transaction, right? All this has to happen in milliseconds, and quickly they have to write rows. And the format they use to write data is usually raw format because they don't have to do any conversion. They quickly enter that in the storage, and next block they quickly enter the next row. So that's the reason this is mostly raw format. So you have these operation systems, and something, you ingest data and bring it to a data warehouse. Now, why data warehouse? Why do we need data warehouse? Since you have the operation systems, why do we need a data warehouse? Multiple reasons. First, as I said, these systems are designed for write speed, right? And these system works on small set of rows, let's say 100, 200, every time you have to write. In data warehouse, you have to work on millions or sometimes millions or billions of rows, because let's say you have to analyze, in this case, return rate, right? Return rate is sales returns over dollars. Let's say you have to compare year over year growth. So you have to look data for past 1 year or 2 years. That means you're working on millions of rows. in case of a bigger company like, yes, as you said, centralized data. And second thing is like, since the systems are separate, returns, let's say you have to calculate return rate, right? So you need the returns data as well orders data, right? So you have to get data on a common platform to join. It will be tough here. First thing is, right, it is designed for read speeds. And second thing is you have to bring data to common place, centralize the data. And third thing is, if you query the if you query the operation systems, you're going to impact the operational performance of the enterprise, right? Basically, there could be impact to the slowness in the order taking capability, right? So you want to make sure that you run your queries or processing on the separate system which is designed to handle that kind of volume. So first is basically the system are designed for read speeds, the data warehouses, whereas the OS operation systems are designed for write speeds, because they work on very small number rows. Second thing is centralized data. You want data at a common place. And third thing is you don't want to impact the operation system. You need something separate, which without impacting the operation system, because then your order taking capability or the website may slowness may occur, right? Because if you transfer everything, all the load for this high compute system where where you're working on millions of rows, right? You don't want that to be happening here on the systems, right? Okay, so this is like a data warehouse, right? So now we know why we need data warehouse. We need a centralized place. So basically, you ingest data, you do that ETL, you bring that data into a common place, design a dimensional data model, and start reporting out of it. So this was a very popular architecture in 1990s, 2000, early 2000, when data was structured. Basically, you did not the data was volume was less, it was a structured form of data. So all these commodity companies like Teradata, Netezza, Greenplum, right, they were very popular, and they had this data warehouse solution. And this was a common architecture which every company used to follow. They used to bring, and the role also was known as ETL developer, or to basically who used to work on extracting this data. What happened around early 2000? So early 2000, the era for big data began. Internet became more popular. The volume of data, the variety, the velocity at data was getting generated bumped up by huge volume. The variety, there was social media picking up. The unstructured data generated was huge at that time, right? So everybody was looking for this. Data warehouse system was not able to scale, or the companies had to keep on buying nodes, and these were based out of proprietary hardware. You understand proprietary hardware? The proprietary hardware is something like they have to buy that nodes. Let's say it's a Teradata system, right? They have to buy that hardware from the enterprise directly. Like in this case, they will ask, okay, my system, my sales have increased. People are now coming online more because of the internet growth. So I have to buy more nodes next year. So okay, let's call Teradata. Teradata, can you install more nodes? So they will have their own hardware, and they will send their own people to the everything was on prem. They will set up the nodes. They will reorganize the data, and they will send a big bill to the enterprise. So this was very costly. So every company now needed something better which could handle unstructured data. So then came the architecture of a data lake. So you had data lake in the middle, also known as two-tier architecture, and you had data warehouse in the end. And this was being reported. So data lake, all the unstructured needs, this data lake could support unstructured data, high volume of processing, machine learning use cases or AI use cases started. That was also picking up during that era, started running on this data lake. And all the workloads for processing, cleaning, transformations was transferred from the data warehouse to the data lake. When data was all ready, it was transferred to data warehouse for reporting out of it. So this was architecture very common around 2010, 2011, 11. So this architecture became popular. So when basically internet was growing in 2005, around 2005, Google published a paper on Google file system, right? Because Google was the first company which was kind of going through this huge growth of data because internet was getting more popular and they needed some solution. So they developed internally something known as Google File System, which they published a paper, and that paper was picked up by Doug Cutting, who was a Yahoo engineer at that time. Similarly, Yahoo was a very popular company. Yahoo Messenger, Yahoo Chat was very popular, and that had a similar problem where data was growing humongously, and they wanted something to solutionize that. So internally, Yahoo developed something known as Hadoop, and they made it open source around 2011 or 12. And when the data lake concept came into existence, companies started moving on to this architecture where they could use transfer all their workloads to data lake. Support for unstructured data used to come. It was able to handle huge workloads. This was basically designed for batch processes, and machine learning use cases also started supporting it. So now I think you guys might have a question, right? If we have a data lake, why do we still need a data warehouse? Why data lake? Why can't we directly run our queries on data lake, right? So that was the question you guys might have. Any idea like why we still needed a data warehouse with this architecture? Okay, I will go ahead. Okay, I'll go ahead. Yeah, so the problem with data lake was the data lake, although was used to handle unstructured data or some data processing, it was it was not designed for concurrent queries. First problem was concurrent queries. Like let's say data warehouse, let multiple users accessing. It was designed for batch processing. Like when you're processing overnight data, and then in the morning when data is ready, it is being consumed by end users. So that kind of workload, the data lake was not designed for that. It was not able to, like, multiple people are querying the it used to slow down. It used to not handle data workload because it was mostly written in Java, and it doesn't supported that concurrent queries. Second thing was it was not so much asset compliant. Like asset compliant was a problem at that time, and then it did not support the merge and updates very well. So to do that merge updates, you still need data warehouse support, where you transfer the data, do that merge update, finally data is ready. But the good thing was that you had transferred most of your workloads or most of your processing on the data lake. So now at that time, like when data warehouse was a proprietary appliances, right, where you had to buy, spend huge cost to the companies like Teradata, Netezza, to basically buy more nodes. Data lake was all built on commodity hardware. To understand commodity hardware is basically commodity versus proprietary. Commodity is something they have to, you can buy those servers from the market, and you can just install the components, Hadoop or whatever, the open source Spark on the data lake systems, and then process your data. So that way this was cheaper, and you can scale it as your data volume increases. You can scale your data lakes as you want. I will take one question. Are you referring to problem concurrent in data lakes or data warehouse? Concurrent problems was in the data lake. Basically, the data lake was not able to handle concurrent queries, and it was not designed at that time. It was not designed for update. It was not designed for update inserts. So now after this, there came a concept of Kafka. I think you might have heard about Kafka, right? Which was a layer sitting between operating systems, and data lake. Any idea like why we needed Kafka? Why Kafka became popular? So Kafka became popular because of the growing needs of the real-time use cases. That was one reason. People needed some real-time support. They needed real-time because this was a PubSec kind of system. Data used to get published on the Kafka with for a retention period. It used to stay there for some time, and whoever want to ingest, they can ingest. Second thing, that second most important reason was that other than the data lake, there were other consumers of the data as well. Let's say the email system, right? When you place an order, it does, you also get a confirmation email, right? So this email system also has to read the data from the orders to send an email to the customer, right? Marketing system, let's say recommendation engine, right? So recommendation engine, so let's say when you shop from Amazon, when you order something, let's say I ordered a shirt, right? It recommends next time you log in, it recommends you, okay, why don't you buy this pant? or I ordered a razor, why didn't you buy the shaving cream, right? So that recommendation system also has to be real time. It cannot wait for batch processing for data lake and data warehouse. It has to hit the operational systems to basically look for that data and do that recommendation engine. So Kafka was introduced to handle streaming use cases or real time use cases. Plus, it was basically handle that load. You don't have to hit the operation system every time because this is very critical. It used for day-to-day operations of the company. So rather than hitting the operation system, you just hit the Kafka. The operation system will write to Kafka once, and all the systems who need data can directly access from Kafka. So Kafka became very popular. So this was a most common architecture around 2013, 14, 15, 16, and I think this architecture is followed by companies on the cloud currently also. I see many companies, many big enterprises are following this kind of architecture. Now where we are heading, like what's the current architecture, most popular architecture, and where we are heading. So let's draw operation systems, and you have the something known as lakehouse. Anybody heard about lakehouse? Lakehouse. So what is a lakehouse? Lakehouse is a combination of a data lake. It's data lake basically. Data lake plus a data warehouse. So basically, lake coming from the data lake and warehouse house coming from the warehouse, right? So basically, it's a lake house. So remember, what were the problems with the data lake? The problem was concurrent handling. It was more designed for batch processing. Secondly, it was not so asset compliant, and thirdly, it was not designed for update inserts, right? So lakehouse major players like some for five major players like Databricks, One House, and Tableau, which is now acquired by Data. They worked on some file formats. So basically, Delta format, Hoodie format, Iceberg format became popular at that time. Became popular. They started dwelling. So all these formats are basically how you store data in the storage in the backend in your storage. So the storage component. So they kind of started supporting those update inserts well. They were asset compliant, right? And the problem of concurrency, right? What they did, they developed something known as a different compute engine. So since the processing is the processing or reporting has to happen through compute, right? So they separated the compute for the lake, the data processing, and they separated the compute for the reporting. So I think Databricks introduces something like a photon engine, and where which was written separately, or SQL data warehouses, where the reporting has to happen. When you're processing when you're doing batch processing, you use a different compute. When you're reporting, you use a different compute, photon, which is more focused on the concurrent queries or reporting data sets. And that way, it's basically going through the original era like a data warehouse with that added thing to handle that big data velocity, variety, volume, and support for ML. And then you also don't have to move data to a separate system. So basically, this is the most a similar kind of architecture which we had in the early eras, but with added support for everything in terms of volume, volume, and also support for ML use cases also happening, and storing unstructured data and everything was to able to. Um, okay, so now I'll go back to my slides. I hope this gave you an overview how we have evolved over years from a data warehouse to a lake house. So let's go to next part. I think we were here, right? Yeah. So this was this a slide deck, right? So this is highlighting that data warehouse initial era. Like you have structured data, everything was structured data, important data was unreported easily, and this was a two-tiered architecture, mostly common around 2010 until now. I think company uses this kind of architecture. You have a data lake where you have a raw store of data, some processing done, and you transfer the data to a data warehouse, and then you report out. Machine learning and data science use cases happening through a data lake, but the BI and reporting use cases happening through a data warehouse. Right? This was the era around 2010, 11, 12. Until now, companies follow this kind of architecture. So now this is more popular architecture where you have structured data, semi-structured data, unstructured data streamed and batched over to a lake house, and you use a common system. Data is not transferred to a data warehouse or something. Use a common system by maybe using different compute engines specialized for batch processing or reporting, and you kind of power all your needs, either BI reports or AI use cases or data science or machine learning. You're able to see my screen, guys, right? You're able to see lake house layers, right? You're able to see the lakehouse layer slide, right? Okay, thank you so much. Now let's go to, yeah. So now the next session, the file formats, right? I briefly touched based on this, right? So this file formats like Hoodie, Iceberg, and Delta Lake, as we know that, right? The data lake was not designed for, it's mostly the formats for ORC and Parquet, right? ORC, they were not supporting the asset compliant initially. They were not designed for updates and merges. So companies started, people started working on, since it was open source, people started working on different architecture, and these were more popular, like the Hoodie was a format which started, all these basically are designed for common use cases. Like all of them support schema evolution. I hope you guys understand schema evaluation. I think there's a question. Asset is basically asset integrity. So basically that's the way, like update and to maintain the integrity of the data set. It's a simple terminology. Basically, let's say you can just Google it. It should be very easy. Like basically, you need to maintain that integrity of the transaction when you're doing the transaction. Like all updates are done together and systematic on the system. So basically now these formats are developed to support ACID compliant, to support updates well, update merges well. Moreover, they supported schema evolution, time travel. Time travel means, let's say if you want to go back and see what was my state of the data at that time, they supported this very well. So all these three formats of data have a common, like mostly common use cases support in terms of streaming data or schema evolution or supporting the time travel. You can use all these three formats. There are some differences with how they store data, and some are powerful in either streaming, some are powerful in batch processing, some are powerful in reporting. But I think there'll be minor differences in terms of all three are pretty very good formats to use for any use cases. So these are the high level differences of Apache Iceberg, which was basically developed at Netflix by Apache, and then basically it excels in this Apache Iceberg, which excels in large scale analytics, right? When you have schema evolution, like when the source system adds column or changes schema, right? It's automatically propagated to the downstream system. Similarly, Delta Lake is mostly coupled with Databricks, right? Whenever you have a Databricks system, they use mostly the Databricks. They mostly designed for Spark, but now it has support for other engines as well, like Flink, EMR, and it is used for streaming processing. Hoodie is again designed for streaming data and frequent update. Uber, I think there's another company like OneHouse who kind of is kind of focused on Apache Hoodie. And so these, I think, with Lakehouse and these formats, we have that a problem of concurrency and the update insert and asset compliance supported. And we added tons of more feature like time travel, schema evolution with these file formats. So why do we need real-time pipelines, right? So real-time pipelines cases are picking up. Most of the case, most your 99% of your use cases, like the BI use cases or reporting use cases, was solved by the, like even in my previous experience when I worked at companies, right? I very rarely there was a need to develop a real-time pipelines, but now with the recent years, right, these use cases have grown up a lot, and I think there are many companies where they need real-time pipelines, right? So majority of the use cases like fraud detection, right? Fraud detection, you need to block and identify transaction at real time, right? So you use that for, you have a real-time pipeline where you quickly quickly have to detect fraud, block that fraud. So in that case, you will use real-time pipeline. IoT sensor data processing, like in big manufacturing firms, like where you have big machines, right? You want to make sure the conditions are safer for my people working in the factories, in the machine, working on big machines, right? So you may need to monitor some IoT data in terms of if that, let's say, something is wrong with some machine or something, right? You need to make sure the real time that hey, some alert or something should come to you as a company facility, right? Where you can make your workers safe who are working there. Customer experience, right? Anytime you log into your Amazon account or Walmart account, wherever, you need to have real time updates, your tracking, or those things, right? For that, you may need real time pipelines. Real time one common example is when I this example from, I think, when used to work at Walmart, right? So wrote a real time pipeline where you had to basically report Thanksgiving, right? Thanksgiving, Thanksgiving sales, right? So there you ingest data from your source system. So real time reported to the executives. So they wanted to know what's my inventory, how are my sales going every 15 minutes, every 10 minutes, or how are my inventory depleting? Do I have to basically, let's say, whatever product they have put on sale, do they have to replenish the inventory on the stores, or is my Thanksgiving sales according to my forecast, right? So they need that real time analytics on dashboards. That could be, again, for supply chain real time tracking inventory. You need to be very, like, as soon as the inventory is depleting, you may want to place an order with a supplier or vendor. Hey, this is my inventory, this my item is depleting, can I get more of, watch which products are getting sold more. Real time you may get that information, and you would not having issues with your basically your sales will be more, right, if you have proper tracking and you can source the item well on time. So let's move forward to key principles of pipeline design, right? So when you design an ETL pipeline, when you are ingesting data to a data lake or a lake house, right? So you have to build a pipeline. You have to do ETL, extract, transform, load, and you have to build a pipeline which is different components. So the key principles of pipeline design are, let's start here, like modularity. Anybody understands what modularity is? So modularity is something like where you design your pipeline into small modules, right? There are two options. Either you can, let's say, you're extracting data from source system, right? You're writing it into a data lake, and then you're processing into a data warehouse, right? In the data lake, you might have some processing, you might be doing some transformation, some data cleaning, right? I think there's a question. Pipeline. A pipeline basically is an ETL, extract, transform, load, where you ingest data from the source, as I explained, right, from the source operation systems, right, and or which could be by APIs, or maybe by basically some writing some ETL. It could be an API processing from some API environment. Basically, you write code to process, to ingest the data into a data lake, and then you also write a code to process that data, clean up the data, make it ready for people, for to add value to it, for people to report. All that is done by an ETL pipeline. And that pipeline, you pipeline has to be modular. Modular means you have two options. Either you can have a one big piece of code which does everything, extracts data, cleanses the data, transform everything, and then finally loads into data warehouse. Or you design your pipeline into small modules. Let's say for extraction from source, you design one small module and write it in raw zone. Raw zone to cleansing or transforming data, you write another small module. From cleansing to final dimensional model, you write another small module. So basically breaking your pipeline into small steps with small pieces of code, which has small pieces of code. So which is a better design? A big code with everything to final layer, or you want a modular pipeline? Yes, we want a modular pipeline. The reasons for it, let's say there's a failure, right? So if your pipeline is not modular, you have to scan through the entire piece of code. Your restartability will be impacted. Let's say you have to restart, it's failed, and you have to restart from a point of time. If it's a big piece of code, it runs everything again, right? So your restartability is easy, your debugging capabilities are easy. So you need to make sure your pipeline is modular. You can start from any point of. Restartability is similar. I covered in modularity. Basically, your pipeline should be designed in a way restartability. Let's say your job failed at step number 3. right? You should be able to restart from step number 3 without running step number 1 and step number 2 in the ETL pipeline. And it should be restartable without corrupting the data. Like it should not create duplicates, or it should not create any unnecessary merge or updates or inserts, right? So you need to make sure you handle that. You have a piece of code to check that, either by not exist or deleting the data you're processing first. You should be able to handle that. You should design your pipeline that way. Third thing is backfilling. What does backfilling means, right? Backfilling is something like where you, let's say when you're designing a pipeline, right? Let's say you have orders data and you're bringing the orders data for the first time, right? And you may not have the source system or the operation systems has order data since let's say your company went live in 2010, right? But you're writing it now 2025. You don't have 15 years of data in the data warehouse, right? Let's say, or maybe some other, another table you're bringing into data warehouse or data lake, right? So when you build your pipeline, you need to ensure that same pipeline should have capability to ingest. That's a good practice. Basically, you the same pipeline should be able to process your historical data as well as same pipeline you can use for incremental processing as well. Maybe you can switch the parameters. Or let's say let me give you another example. Let's say you're running your pipelines in 6 months. 6 months you find out an issue. Oh my! Let's say you started that pipeline running in January, and in September now you find out issue that the data for March was incorrect. Some business user reported that, and you said there was a small issue in the March pipeline, and somehow you have to process the entire pipeline again for March, just for March. So your pipeline should be, rather than writing that ad hoc piece of code, your pipeline should be flexible enough. Just by passing parameters, you should be able to backfill the March data. So you have to design in a way that's a good practice. Otherwise, if you spend time another piece of ad hoc piece of code to handle that March data, it will take your development cycle, and it may not be a good practice. So you all need to design that pipeline in mind, that at tomorrow, if I have to backfill the data, I should be easily able to do that by passing those parameters. Yeah. Idempotent pipelines, right? I think idempotent pipeline, I briefly touched on that. Idempotency means like when, if let's say you when you develop pipelines, right? Somebody supports it. There's a team who runs your pipelines every day. Monitor is right, third party, the third team. You develop it and you give it to the daily operations team, which kind of monitors your pipeline, your supports them with business users. So let's say somebody ran that pipeline twice, maybe due to a failure or something, they ran it twice, multiple times, right? So your pipeline should be idempotent in the sense that it should not it should not corrupt the data. It should not introduce duplicates. It should not introduce any unnecessary updates or inserts or merges. It should basically, the data integrity should remain intact. As much time you should run your pipeline. You need to have those controls either by not exists on primary keys, or either by deleting the data. Let's say if you're processing for a month, you should delete the data for the month if you're running for a month, and then run the data again. So you need to ensure that your pipelines are quite important. By mistakenly, if somebody runs multiple times, your data should remain intact and clean. No issue should be introduced. Code reusability. So when you're building your pipeline, make sure, like, ensure that there's a component you wrote. Let's say you wrote a component, or maybe some API you're pulling data. If you have to pull that data from API again and again, and maybe some other person in your team has to pull the data from the same API, you can write some reusable component for that, and you should submit it to a common repository or common folder in your repository, where any reusable function, or and you should do some reusable framework as an enterprise. Can you guys hear me? I see a comment from Kevin that I am muted. Okay. Okay. So yeah. So basically, reusability means like you should have like in companies you have frameworks to process data. Let's say you're extracting data from source system, or you're processing in the warehouse. You just develop frameworks which are usable by anyone in your team, or anytime you identify an opportunity where you have a common code to develop. You should think about, how do I write, how do I ensure that my other team members or myself in the future may be able to use that code for processing. So you should design that pipeline in that way. Maintenance and debuggability. That means like when you're building a pipeline, you need to ensure that you have proper commands. You should have proper failure exceptions exception in handling in place. So whenever there's a failure happen, it properly flashes this message that this is a step, it failed, and easy for any operation member or maybe not you to understand it, to kind of debug it and resolve it as fast as possible. Because sometimes pipelines have most of the times pipelines have an SLA to meet, and you need to ensure that you fix those pipelines during that SLA time period. So it's very important you write a code which is easy to debug and maintain. And maintain in the sense you should always have a repo, a Git repo or GitHub, and to maintain that code with version, proper control, proper peer review, proper, so that you can always trace back and see where was that that change happened in the pipeline. Readability, as I said, you should properly comment your pipelines, comment your code, whatever step you're using. Maybe leave a small comments and on your pipelines to readability, to have a proper design. Scalability, your pipeline should be scalable. You should design the with scalability, like my pipeline is working for small volume of data. Okay, so will it work for if I scale, if the data volume increases tomorrow to a petabyte or so you should design that mindset in mind. You should have a scalable pipeline. Let's talk about data quality. So we talked about pipeline design. Now we'll talk about data quality, which is very important for any AI use case or any data use case currently, right? So when you design your pipeline, right, you need to make sure the pipeline focuses on data quality, right? You need to make sure your data is accurate, you're free from errors, reflects reality, it is complete, all the necessary data is present. There are no like let's say you load a table, they're like they're null, the null columns, null values are less, the data is completely describes the record or the primary key of the data set. Data set is consistent, it is uniform. Let's say you have multiple source systems, so it should be like a uniform set of data you should pull from that source system. For example, your orders might be coming from multiple sources. Let's say store, in case of Walmart, it may come from a store, it may come from online system, right? And you're bringing it to a common place. You should make sure the data is consistent, you have all the attributes to report it. So timeliness, where data is available whenever you need and up to date. So these are the four foundational data quality. And how do you maintain that? Whenever you design a pipeline, you need to ensure you put those data quality checks. Generally, why my rule of practice is, like when I'm gathering requirements based on my business users, when I'm documenting and designing, making a design document, I do to put together a data quality. I do put together a data quality checks in place. Like I create a small section where I work with my business stakeholders to kind of discuss what data quality checks I can put, and finalize that. Let's say they may say, okay, my return rate. Let's say I'm building a return rate pipeline where I have to report return rates, right? So I will ensure that I put a check in place with regards to um, my return rate has to be between 7 to 10%, a threshold check. It should not go beyond 10%. It should not be less than 7%. So I'll put that check. I maybe one easy check could be I could check that every day I get 1,000 rows for this table. I could also check for null values. Let's say my order needs to have an order ID, right? Order ID cannot be blank. Or my order needs to have a product ID as well. Product ID. Product ID should not be null because you have to sell something for order, right? So all those null checks, range checks could be like my sales today should be within this range. And if anything is not right, if it is more than this or less than this, there's a problem to check. So all these are data quality checks are very important to be more proactive rather than your business users or anyone kind of raises an alarm on the data later on. Your data quality checks make sure your data quality is met, and you are more proactive. If any issue comes, you can easily debug. And there are two type of data quality checks. One is a soft check, and one is a hard check. You understand soft check and hard check? Anyone wants to comment on the chat? What is a soft check and a hard check? Okay, let me explain. Soft check is something like where you don't break the pipeline. Like example, referential integrity, right? You're checking against, let's say, customer ID. Customer ID is not coming in the data. So there could be a late arriving dimension where you customer ID, the customer was a new customer and the customer system data came late, but you have an order transaction from the customer. So next day, your customer ID will be patched up. So that would be a soft check. You just report it out. Hey, this customer ID is null. And tomorrow you can check next day. And if the customer ID is not populated, then it could be a hard check. Hard check means you're breaking the pipeline. Let's say you ran a count check and the volume, the date, there's a zero records in the data being pulled for that day. So that will be a hard check. You break your pipeline and right at that point, and you issue a red alert, and then you kind of debug, right? Soft check is something you continue a pipeline, you do not break it, you populate the data and you report it out via some alerting dashboard, and you debug at your own time, maybe next day, maybe monitor it. So these kind of two soft and hard checks you have to design in your pipeline. So this is clear, the quality. ETL logging, right? So most of the engines now come with ETL logging directly. But let's say you're developing something on the cloud, a framework or something, right? You need to ensure you focus on ETL logging. So whenever you're writing a pipeline, your pipeline data should be logged, like when the job started, when it failed, when there was an error, you should log that. You should have an history of your pipeline running history, where you should be able to track for any scenarios later on. Let's say somebody reported some issue in the past, so you should be able to look at ETL log and say what happened that day which is causing that issue, and maybe correct it, maybe brainstorm and maybe have that retrospective to make sure you fix that data scenarios, and you kind of figure out that gap. So ETL locking is very important. So either by a framework, you may write small components which you plug in into your pipeline at starting and ending, and basically for starting and logging time, or maybe an error, basically you can ingest that reusable components in your pipeline, and so that it logs your failure, logs your time failed, your error, everything is logged properly, which will be helpful when you're reporting it or analyzing or debugging any issue later on. So ETL logging is very important. You should consider that when you're designing your pipeline. Data governance. Data governance is another, when you're designing your pipeline or when you're designing a system, data pipeline or data lake, data warehouse, data governance is very important. It is needed to establish standards. You need to ensure right now there's a lot of hackers around, so you need to make sure the data is secure. It is not accessed by anyone, even within a company, within an enterprise, right? You need to ensure that the data is accessed by the right team. Let's say your HR data should not be accessed by only by HR team. It should not be available for any other users in your company, right? So you need to ensure that, and even financial data you need to secure to the finance users, or maybe some users in the company may not be entitled to look at finance data, right? And similar case with HR data is proprietary for HR people, right? They should not be looked by any other, in terms of. So you need to establish proper governance, set up proper tables, proper access, right? And we need to ensure right people in the right team have access to the right kind of data. So right, make sure when you're designing the pipeline, there might be use cases also. Like I developed something in the past where you had to report commissions, there in any company, right? In the sales team, there are people who sells the product, right? Sells the software, like if it's a software company, right? So every sales guy has a commission for selling that product, and every person will get a different commission based on how much product it has sold, or how much the company has gotten revenue based on that sale, right? So that sales data, commission data, should only be accessed, that I should not in the company. I should be able to, like if I'm the sales guy, I should know my commission. I should not be able to see any other commission, right? Or similarly, or my manager should know my report is my commission. My other manager should know their sales team commission, right? So that data is also very secure. So sometimes you have to develop something where a pipeline where you have to go to a row level access. Like if your data is common, like commission is stored in one common table, one row might be accessed by one sales guy or AE, account engineer, or another row might be accessed by different sales engineer. So that you may have a row level security as well. So it's very important. You need to think through when you're designing your data pipeline, gathering requirements. You need to ensure that you just make sure you should not open data for everyone. You should have those controls in place where data is accessed by the right team and the right times. And if you do not do that, there could be incidents like sort incidents where your data is exposed to unnecessary people, and it is creating issues, right? So auditing, you should always audit your data. You should have auditing in place where you check who has accessed the data, some auditing reports, some auditing checks in place to make sure to correct on if somebody who is not supposed to access the data has accessed the data in the past. You should have those logs in place to ensure that you keep on correcting your governance and securing PI data. Again, you need to ensure your PI data is secure. The CCPA and some European policies, you need to ensure that this data is not openly available. The customer information or name or all these social security number are secured well or kind of masked before they are exposed to data. Single source of truth. So whenever you have your data, you, let's say you, there's a revenue metric, let's say sales should be a common metric across your organization. It should not be like sales, so your finance team is defining sales differently, and your another team in the companies is having a different definition of sales where numbers are different. So across the enterprise, you need to have a common source, a single source of truth. Do not have multiple tables when you're designing pipelines. Don't have multiple small tables. You need to have a consistent dimensional data model, which is common for the entire enterprise, right? Where people can just have single source of truth, one table for the information. And maybe you need to also maintain a KPI kind of document, a centralized repository where you define your KPIs and make sure multiple copies of data are not available in the while you're building this pipeline.
There's one question I want to address. I think Priyanka had mentioned the prices when it says starting from, the prices starting from does not, there are ranges. For example, somebody has to prepare for, let's say, an engineering manager sort of a career, or somebody wants to prepare for, let's say, a different sort of a career. It's based on what domain you choose, what curriculum you choose, what project. So you build it with your program advisor, for lack of a better word. Uh, Oleg, I will share. Sorry, over to you, Sachin. I think this is it. I'll share the link in the chat as well, folks. Here is the link. On the chat, I hope you can see the link. Over to you, Sachin.
Okay, so I think the next section is ETL and DA interviews, right? So when you have a DI data engineering interview, right? Uh, so what key concepts you should focus on? Um, so solving a business problem, need by ETL. Usually they will give you an example. They will ask you a design question, or they will give you a business problem and how do you solve by an ETL. So basically, you should not focus on technology tooling, right? You should focus on the core concept, like whatever I explained in my class today. Focus on those and answer from that perspective. You should ask the right questions. So interviewers do assess you, like how do you get details on the problem. They will have your requirements. They will give you vague requirements. So you need to ask the right questions, and they want to test you that how you are able to get to the exact problem they want to ask you. So they assess you for that skill as well, whether you have those, because that skill is always important while you're working on the problem also in a regular company, because you want it to get to the, you need to ensure that whatever you need to build this application or a ETL, you need to have all the right information to have everything what I explained in my class, like data quality, governance, or you need to basically, that's the thing they test. They basically want to test you how you interact, how you do that shared collaboration with other teams. So need to develop that skill as well. So how do you demonstrate ownership of your data sets on behalf of your scale? Basically, you should understand your whatever pipeline they assess you. Maybe they give you a sample pipeline, or maybe they ask you, maybe in the later rounds when you meet a manager or something, they ask you about your pipeline you build. So ensure that whatever examples you have, you understand that pipeline end to end, understand the business functionality of that, rather than just knowing what is being done. You should understand the end case, use case, why we are building that, what's the use case, what we are reporting, what KPIs. So these concepts are very important while you are preparing or thinking about a D interview. So let's go through an interview case study, right? How do you design a lakehouse based pipeline to analytics dashboard for a retail store? So this is an example, for example. So you have a lakehouse based pipeline. You basically, in this case, you see the, as I explained, right? You have an operation system, right? After a data is maybe the customer has purchased from the retail store. It is basically got into the Kafka from all the operating systems, and via Spark data processing, it is brought into a data lake. Basically, data lake, it could be a data, it could be a lake house. In this case, you have governance, you have all the other system data, you ensure data quality is there, you have the metadata, all the information, and you power the analytics dashboard, and you report it out of it. So you could also have a batch processing. You could directly, there could be an architecture where you directly process from the operational store rather than having Kafka in the middle, and you could also process that into this is a high level flow of data. I think it's similar to what I explained in the previous slide. So whenever you answer that in terms of, you have to plug in those capabilities, that how do you design, how, what are the key pipeline design criteria, the modularity, the idempotency, all you have to talk through here. You have to talk about data quality. How do you maintain the data quality of a pipeline, right? Even you have to talk about the analytical capability. You should know your pipelines in this case, right? You need to talk about your, like, what KPIs you are building. You have to talk about data governance. I talked about why do we need data governance. So this is basically just a sample example, but you have to plug in all the um, previous concept which I talked about in my class. Right? I think Rohan, this slide is you, right?
Uh, No, Sachin, I think this is if you want to take it up, take it. If it's not, then let it be.
Yeah, so
No.
data engineering to 2025, right? What it takes to be a data engineer in 2005, right? You should understand the concept data lake, warehouses. You should understand observability, the real-time pipelines. The AI is very important. You are designing, you're building pipelines for AI systems as well. So you need to, and I'm aware of those use cases as well. The key skills you need are SQL, the Python, ETL, data modeling is important as well. You have to design the data mission model and ensure you understand they usually they will give you they will start with a business problem, and they will ask you to design a data model, and then over that they will ask you SQL and Python question. So that's how the trend is. So you need to have these also cloud and infrastructure expertise is also good to have. Like if you have AWS, GCP, whatever, any couple of cloud or maybe a cloud information, and even the orchestration tools, like sometimes they use data factory to process, or airflow, or all these tools to process the data. So having some knowledge around that, but my weight is on the concepts, which is on the right side. If you know these concepts well, the tools are vary across the organization. So this could be important, but I would weigh the right side more in terms of. And then AI is, as I know, the AI and ML is picking up. Everybody is looking for LLMs, agentic AI. All these concepts are becoming popular, and this gives you an upper edge if you have these kind of concepts also in being a great engineer, data engineer. If you have these add-ons, and then you become a full-fledged complete data engineer where you have all this knowledge as well.